Thank you. Can you hear me? Okay, so well, first let me thank the organizers. It's a pleasure to be here and talk about work that I actually started doing in the middle of town in the old dump building many years ago. Okay, so I'll tell you a little bit about scaling properties of various types of defect networks. And so this is work I've been doing with lots of people in this room. I also want to highlight the work of 3 students in Porto. So there's Mafalda, who's now at École Polytechnique in Paris, and Andrea and Miguel Oliveira. And when I discuss numerical simulations, so some of them have been done in Cosmos, just sitting just next door, and some of them have been done in Milipeia back in Portugal. Yeah, so we now know that scalar fields are part of the building blocks of nature, and the immediate question is whether or not these have a role in cosmology. And cosmic defects are a possible signature of these types of fields. So you've seen these pictures already in Paul's talk. So here's a field theory simulation of a billion strings. Here's an analogous type of string network in a liquid crystal. This is a different type of defect that you might see if you go to the seaside. You can also see them if you go to Mars. So these are called taphony usually. So what I want to do is to find analytic models to try and describe the evolution of these networks, and in particular look for scaling solutions, i.e. late time asymptotic scaling solutions. So throughout this talk, when I say I'm going to look at defects in cosmology, so when I say a defect network is scaling or is not scaling, what I mean is this scaling invariant linear scaling solution where there's a characteristic length scale that's growing as t, and there's an RMS velocity that's constant. So the network is evolving as fast as is allowed by causality, essentially. And so I'll be discussing expanding universes. So in most cases, the scale factor will be growing as some power lambda of physical time. This is important, especially if you want to simulate defect networks. Some of the solutions I'll describe only exist in expanding universes. If you simulate them in Minkowski space without expansion, you may not find these solutions, or you might find different ones. And as I already said, so I'll be discussing cosmic defects, but many of the solutions that I'll discuss exist in analogous systems in condensed matter, and this kind of formalism that I'll describe, as Paul also already mentioned, can be applied and has been applied to condensed matter. Okay, so here's how we model them. So the idea is you sort of abandon the idea of doing statistical physics and start doing thermodynamics. So you know, or you assume you know, the macrophysical evolution equations for these defects. So you choose some set of average quantities like correlation lengths, RMS velocities, and then you use the knowledge of the microphysics to derive average macroscopic evolution equations. And then you just study those. Of course, you pay a price. You're going to have to introduce some phenomenological parameters which you cannot deduce ab initio. So you still have to go back to simulations to calibrate these phenomenological parameters that you've introduced. So as I said already, so I'm going to be interested in essentially 2 kinds of quantities. So a characteristic length scale, which you can think of as a correlation length or as a curvature radius, or just as a measure of the density of the network, and then RMS velocity. Of course, for more complicated models, you can introduce additional degrees of freedom and sort of extend your model. So Paul showed you already the equations for the case of strings. I'm going to write them here in a slightly more generic form. So for defects with n-dimensional world sheets, so n equals 1 is monopoles, n equals 2 is strings, n equals 3 is domain walls. So you can define the characteristic length scale as a function of density like this. So eta is the symmetry breaking scale. And then you have evolution equations for the characteristic length scale and for the velocity. So important parameters here are the Hubble parameter h, which is just a dot over a being the scale factor. So up here I have, so this is essentially Newton's second law. So I have driving forces that accelerate the network. I have damping forces that slow them down. So the driving forces here could be curvature for the case of strings or walls. It could be long-range forces. It could be other things. Then I have a damping length scale, which includes the effect of the expansion, so Hubble damping, but it can also include friction due to particle scattering or other effects. And also there's a term here that accounts for various types of energy losses. Now, of course, the way I've written the equations here, they look very simple, but all the art in this kind of modeling is to figure out the specific form of these terms for the defect you're interested in. And of course, you have to try and make sure that you're modeling the defect you're interested in properly. Okay, so let me take you through some particular solutions for particular kinds of defects. So you can start with monopoles. You can confirm, so the advantage of this model is that it allows you to treat these kinds of evolution scenarios accurately. So in particular, you can confirm lots of work that people have done in the past in more sort of qualitative ways. So in particular, for local monopoles, you can confirm that their evolution is very sensitive to the kinds of annihilation mechanisms you have. For global monopoles, generically they scale, and as far as you can tell, some simulations that have been done quite a long time ago agree quite well with the modeling, so it would be nice to have sort of larger simulations to calibrate this model in more detail. Then you can have hybrid networks where you have monopoles attached to strings. These typically annihilate very quickly in less than 1 Hubble time after you form the strings, although you can in principle fine-tune model parameters to make them survive for a bit longer if you so wish. Then you can have models where monopoles are attached to 2 or more strings. So these are usually called necklaces or lattices. Usually these scale, although again, you can find other regimes where you have other solutions at the cost of fine-tuning some of the parameters. Then you have cosmic strings. So for the moment, I'm talking about plain vanilla Goto-Nambu type cosmic strings. So there's an attractor linear scaling solution for large scales that's been well established and confirmed by pretty much everyone that simulates them. What's not so clear is what happens on small scales, loop distributions and so on. And I point out that you can have the network scaling at large scales without it scaling at small scales, so the two things are conceptually separate. But here already you start seeing that you need additional degrees of freedom. So these are the wiggles that we were discussing earlier. So I have 2 quick examples here. So this is what you find. So this comes from Goto-Nambu simulations. So here you have the fractal dimension of the network as a function of scale. So on small scales, they're straight. On large scales, they're Brownian. So they're like random walks. But look, notice this is the scale relative to the correlation length. So networks are only Brownian basically outside the horizon. At the scale of the correlation length, they're not Brownian. They're sort of self-avoiding random walks. Now, another important feature is, and I think this is part of the reason why you get this factor of 2 difference between field theory and Goto-Nambu simulations, is that if you look at the behavior of, so if you see how velocities are correlated along the strings, so you'll find that around the scales of the correlation length, string velocities are anti-correlated. But this crucially depends on the expansion rate. So if you simulate this in flat space, you see no anti-correlation. If you do, so that's the dotted line here, which you probably can't see, but it's this one. So the dashed one is what you get in the radiation era. The solid one is what you get in the matter era. So the faster the expansion rate, the larger the anti-correlation. This is, physically, it's easy to understand. It has to do with intercommutings. And this is easy to see in Goto-Nambu simulations. It's very difficult to see in field theory simulations. It's very difficult to measure velocities in field theory simulations. I can just about see this effect in domain wall simulations, but no one has seen it in field theory simulations of strings. So I think this is one of possible explanation for this factor of 2 we're talking about. Now, in these things, I'm assuming a constant expansion rate. Now, in the real universe, you have a radiation era and a matter era and so on. So the expansion rate is not constant. So this is important if you want to do really precise quantitative calculations. So in fact, in the period of time that's relevant for CMB, a string network is never exactly scaling. So here's a plot that's similar to the one Paul showed. So this is correlation length divided by horizon, essentially. So this is time in logarithmic scale. So you have a scaling in the radiation era, then you have the radiation matter transition, and the network could be about, I mean, this is very close to today. So the network would be just around redshift 1 relaxing to the matter era scaling. But then you get lambda dominated. And if you're a lambda-dominated network, doesn't scale anymore. So all throughout this time, the network is not exactly scaling. It's almost scaling, but it's never exactly scaling. So if you're looking for % accuracy or something like that, then you have to take this into account. And just a comment that's also related to something that was discussed this morning. So string network evolution is essentially to do with energy flow from large scales to small scales. So you have strings coming in from, let's say, outside the horizon, and then you're losing energy on small scales by whatever mechanism. So this is very similar to a Richardson cascade. Okay, then we have semi-local strings that I already mentioned. So here, there is also a scaling attractor, at least for some range of parameters, but you also have situations when the network doesn't scale. So there could be situations where all the network disappears. There could be situations where both the strings and the monopoles scale, and there could be situations where the monopoles disappear and you end up with Goto-Nambu strings. So this is something we're looking at in more detail. So we have tested analytic models against some of all simulations by John Urrestilla. So we have larger simulations now that we're comparing at the moment. Here is where issues like measuring velocities become important, if you want to characterize them. And I also noticed, just as a passing remark, that you can also describe these types of networks as having two types of strings. So there's the normal strings, and there's some sort of gradient strings that account for the fact that segments might want to grow and join other segments. And this sort of is analogous to some extent to superstring networks. Just before I get to those, let me make a small detour to talk about domain walls. So this is an example that I like a lot as a toy model because it's just so simple to simulate. Here again, a large scale attractor has been established. So here's 3 examples of simulations done in the radiation era, matter era, and another era with a faster expansion rate. So these are 2048 cube simulations, and you can calibrate your analytic model. So this is a parameter C that has to do with energy losses, and a parameter K which has to do with curvature, and you can measure these quite accurately from the simulations. Now you can ask yourself, how robust is this scaling attractor? So I've been talking about relatively simple models. What happens if I complicate the models, put in additional degrees of freedom? Do I still get scaling? The answer is, in most cases, yes. Scaling is quite robust. So in particular, you don't even necessarily need explicit energy losses to have scaling. I mean, this is an old result. For example, for cosmic strings in the matter era, you don't really need to produce loops for the network to scale. This has been known since the 90s. So you really need energy losses if lambda is greater. Oh, sorry, you don't need energy losses for strings if lambda is greater than 1/2. So you do need energy losses for strings to scale in radiation, but not in the matter era. There's a similar result for walls. In this case, the threshold is 1/4. You can think what happens if you have like an additional degree of freedom on the string world sheet, like a charge. So Miguel Oliveira has been looking at that, and essentially you find that there's 2 regimes. If the expansion rate is large enough, charge gets diluted away and you scale. If the expansion rate is small, then charge stays on the strings and you don't scale anymore. Correlation length grows more slowly. The transition between one regime and the other depends on the energy losses and depends on the expansion rate. So what you have here is essentially the expansion rate at which you get this threshold. So with no energy losses at all, this threshold is exactly at 2/3. It's matter era. But if you have energy losses, then the threshold happens for smaller expansion rates. And so with large enough energy losses, you can even scale and dilute your charge in the radiation era. So that's this 1/2 here. Also, string junctions do not necessarily prevent you from scaling. So here's a model that we've built some years ago, where you have any number of coupled scalar fields, and you construct the potential so that for any fields you have any +1 minima, and all the walls have the same tension. So you have junctions which can be X or Y, but all the walls have the same tension. And these networks scale. So what you have here is, as a function of number of fields, the scaling velocity, which is pretty much constant, and essentially the correlation length divided by the horizon. So here, this goes up to 20 fields, but I've simulated this with 500 coupled fields, and you get the same. You still scale. Also, a hierarchy of tensions need not prevent you from scaling. This, again, it's not a new result. There's an old paper by Patrick McGraw, which sort of hints at that. So here's another example of a model where, so we have X junctions and Y junctions. It may not be clear from the picture, but not all of these walls have the same tension, so there's 3 different types, and this network still scales. So essentially, the way I've approached this is I'm sort of isolating various different processes that contribute to the dynamics of the networks, and I'm trying to understand the role of each one of them using toy models, and then I can put things together and see what this implies for superstrings. So here's a sort of summary of where I think things are. So there's some physical processes which I think, or at least to me, so whose role in the evolution is clear. So this includes things like the role of extra dimensions, the role of intercommuting. So lots of people have worked on this, so starting with the work of Tassos Augustidis and Paul. There's also the role of the junctions and monopoles in the dynamics. So all these things, at least in my mind, I think are under control. I think we understand what role they play in the evolution of these networks. Then there's things whose role is not so clear in my mind, and I mentioned 2 of them already. So the fact that you may have additional degrees of freedom, charges or currents and so on. You can have various complex tension hierarchies. There's also this issue of velocity correlations, which I already mentioned in the case of Cotton and bootstrings. Lots of people have worked on this from the point of view of kinematic constraints. I think, so the way I look at this is slightly different. I think the junctions themselves will introduce some sort of velocity correlations or anti-correlations on particular scales. And I think in principle this can be modeled analytically, although it's quite complex. So the story so far is that, well, as far as you can understand, there are regimes where you can have full scaling. So all the network scales with different types of strings having some specific fractions of the whole density. So for particular regions of parameter space, you have what I would call full scaling. Then there's regions of parameter space where only the lowest tension strings scale. And then there's some regions of parameter space where nothing scales. You can have more complex solutions. Now this is a sort of broad picture. Exactly in what regions of parameter space that happens in, and whether or not those regions are realistic is something that remains to be seen. So these are my conclusions. These attractor scaling solutions are quite ubiquitous in these networks, and the reason is just energy minimization, so that's not really surprising. In many cases, if you want to suppress that solution, you have to do sort of slightly violent things or postulate particular choices of parameters and things like that. The way to understand the evolution of these networks really needs a combination of both approaches, so numerical simulation and analytic modeling. In particular, it would be really nice to start attacking the numerical simulation of cosmic strings, or cosmic superstrings. Lots of people have simulated with toy models, but clearly I think better things can be done. And the ultimate goal is to improve astrophysical and cosmological constraints, particularly in the area of Planck, whose data is coming. And I'll stop there. Thank you.
Carlos? I actually have a question. I mean, when they don't scale, then do they start dominating or do they go away?
Oh, for the superstrings, you mean? You could, as far as I can tell, you could have both. You could have, in particular, the highest tension ones. They could decay, or at least the density could become smaller relative to the lower tension ones. But I think there is also some choices of parameters where they could dominate. I mean, it's not, I have to confess, so this is work in progress. I have to confess it's not exactly clear to me where the borderline is, but you seem to be able to find both types of solutions.
Okay, let's thank Carlos again.